Hi, I am Niyati Nayak. I will present results from a pilot study which explored the impact of static and dynamic solar screens on indoor thermal environment and predicted thermal comfort inside building perimeter spaces. This study was conducted in collaboration with Professor Ihab Elziadi. Static screens are non-movable brisoli with optimized designs to respond to extreme solar conditions. Static screens with 30 to 50% perforation and 1 to 3 inches thicknesses are recommended for maximum building cooling energy savings in hot climates. For composite climates that have characteristics of hot and dry, warm and humid, and cold conditions, static screen designs optimized for hot and dry summers lead to overshading during moderate winters. Unlike static screens, dynamic screens are operable and can change their geometric properties to respond to outdoor and indoor climatic conditions or occupant demands. Few investigations on dynamic screens conducted using computational simulations promise their contribution to high building energy efficiency and visual comfort performance. Despite promising results on building performance, their impact on thermal comfort remains unknown. In thermal comfort research, there has been a paradigm shift in the conception of provision for comfort. The notion of a uniform thermal environment continues to be challenged. Scholars emphasize that thermally non-uniform environments within a broader comfort range can lead to occupant well-being and can evoke perception of thermal pleasure explained by the theory of anesthesia. Although there can be multiple techniques to create thermally non-uniform indoor environments, the operability of dynamic screens provide a unique opportunity to design them for creating thermal non-uniformity within the broader comfort range that can potentially induce thermal pleasure in people. The present study aims to explore this opportunity. This study attempts to address the question, which is how can dynamic screens be designed to create thermally non-uniform indoors for occupant thermal comfort and pleasure within an accepted yet broader comfort range. It involved full-scale prototypes in single occupancy office setups in the moderate climate of Eugene, Oregon. Design of the static and dynamic screen prototypes was informed by a sensitivity analysis delineating effects of screen parameters like perforations and thicknesses on predicted indoor thermal comfort in computational environment for summer months for ASHRAE Climate Zone 4C. The static screen prototype was intended to create a neutral thermal environment within the thermal comfort zone, whereas the dynamic screen prototype was intended to create transient environment within the expanded boundaries of the comfort zone. The screen prototypes shaded the windows of the east-facing single occupancy setup. The static screen prototype had 50% perforation and was non-operable. The dynamic screen prototype comprised of two sliding panels, one with 90% and the other with 10% perforation. These panels could overlap sequentially between open and closed conditions. Equipment required to measure the indoor physical environment was placed inside the setup in the occupant's seating position plane. The non-screen, static and dynamic screen conditions were tested during morning hours for the single occupancy setup. The dynamic condition was tested with 3 movement frequencies. Beginning with the open condition defined by O, the dynamic screen panels were altered every 15 minutes or every 20 minutes or every 10 and 20 minutes during a testing hour on a typical sunny day of summer in Eugene. These movement types were named as D1, D2 and D3 respectively. Both static and dynamic screened conditions created an indoor environment consisting of patterned solar patches with higher surface temperatures on the floor and work plane. Moreover, they also created conditions wherein the radiant temperatures varied between a seated occupant's two sides, termed as radiant temperature asymmetry. ASHRAE Standard 55 predicts floor temperatures higher than 85 degree Fahrenheit as the potential sources of local thermal discomfort. Moreover, the standard does not consider radiant temperature difference lesser than 15 degrees Celsius as seen in the tested conditions to be the sources of local thermal discomfort. The quartile range of the PMV values indicate that compared to the static screens, the dynamic screens caused higher variability in the indoor thermal environment by creating transitions between neutral and slightly warm conditions. Dynamic screens with movement type D3 kept the indoor thermal environment neutral for most of the time, besides creating instances of slightly warm conditions whenever PMV values exceeded 1. Further analysis of indoor thermal environment for the dynamic screen setup with movement type D3 revealed that the transition from open to closed position and vice versa decreased or increased the indoor air temperature by 4 to 6 degree Fahrenheit. The drop or rise in the temperature occurred during the early morning hours within 5 minutes after the screen's position change. The dynamic screened condition with an appropriate movement design introduced thermal variability in the indoor conditions that created instances of slight thermal discomfort and comfort. These findings indicate the potential of dynamic screens to evoke thermal pleasure in occupants, which can be explained by the theory of alesthesia. The study suggests an approach to design and employ dynamic solar screens for occupants' thermal pleasure in work environments. This work proposes and emphasizes that designs for external dynamic facade shading systems need to be occupant-centric and should expand our thermal comfort provisions to include thermal pleasure.